Hey everyone. In the last video for this week, I'm going to go through one of the coding examples that was discussed in our required reading in chapter 13 of Regression and Other Stories, particularly introducing logistic regression by modeling political preference, vote choice, based on people's personal income levels in US presidential elections. Okay. As I mentioned in the previous videos, this is a large data set that I included on our Studio Cloud that you can take a look at. There are a bunch of different potential outcome measures, other predictors, additional years, and so on. So feel free to kind of really take a look at these data and run a couple of different models, a couple of different specifications, try some of the functions that we talked about in the past for model fit and model comparison and so on, if you have some time before our Q&A session and before our next topics. Okay. The video for now, or the analysis that I'm going to focus on in this video are very basic. We'll just introduce logistic regression in a simple bivariate framework. What we're going to look at here is this is the subsetted ANES 92 data set that I subsetted in one of the previous videos. So this is just the 1992 US presidential election between Clinton and Bush. And we are going to predict vote choice, so people's support for the Republican candidate for Bush based on income. And income was a measure of different income brackets. This was a 5 category predictor ranging from 1 through 5 for different basically income groups. Okay, so here's a quick data overview. We have our outcome measure, our vote, which just takes a value of 1 or 0 for votes for the Republican versus the Democratic candidate, and missing for abstentions or third party candidate votes. Okay. We have 1,724 respondents in this data set, and we have for most of those respondents, we have information about their income group. Again, this ranges from 1 through 5. Okay. In the previous video, I already showed you how to kind of use the linear probability model, use estimate OLS, and we kind of interpreted that in the first step. And just to kind of first introduce this using basic frequentist, base our functions in kind of in a frequentist framework. We can estimate Logit and Probit models using the GLM for generalized linear models, the GLM command. The way we can do this is by specifying a similar model formula declaration. Our vote is our outcome measure, income is our predictor, which is equivalent to our basic linear regression specification. But the difference here is that we have to specify this link function. And the way we specify a Logit link function for this dichotomous outcome is to specify this is a binomial outcome, so a binomial, or it follows a binomial distribution. The outcome is dichotomous, therefore, and the link function is a Logit. Okay. Equivalently, in order to estimate a Probit model, it's again a binomial outcome, but the link function is a Probit. Okay, and so one will give us logistic regression coefficients, and one will give us Probit coefficients. Okay. The key here is, obviously, these intercepts and slope coefficients are not the same for the Probit and the Logit, but as we mentioned in the previous videos, they are kind of predictably different in the sense that they differ by a factor of around 1.8. If we divide here the coefficients of M3A and M3B, both for the intercept and income, they're about 1.6. So the coefficient for the Logit coefficient is about 1.6 times as large as the Probit coefficient, right? Again, if we, based on this model, then compute quantities of interest, compute probabilities, the resulting probabilities are still the same. These are just differences in terms of the underlying link function. Or if we kind of think about this in the latent variable model, we're basically, we made different assumptions about the underlying latent variable and the distribution of that latent variable. And so we're modeling a different kind of differently scaled latent variable with the Logit and the Probit. But the way these translate into probabilities in the end ultimately will make both of those models equivalent again, at least with regard to their substantive conclusions. Okay, so this is basically just running Logit and Probit using GLM, but of course for a couple of reasons what we focus on in this class is to use Stan GLM, so we directly estimate these models in a Bayesian framework because it allows us to incorporate prior information and also allows us to directly take simulation draws from our posterior distribution, which makes it a lot easier and a lot more streamlined to actually quantify the uncertainty around our quantities of interest. Okay. But essentially, you can now do a lot of the things that we do in Stan. You can do using the GLM functions as well. Okay. So how do we fit the logistic regression or the Probit for that matter in Stan? The specification is basically equivalent. We have our formula that specifies the outcome as well as the predictor. Here we just have income. We again have to specify that this is a binomial, so it's a dichotomous outcome measure, and our link is a Logit. If we wanted to estimate a Probit model in Stan, all we would have to do is put in a Probit here. Same data, and we include this option refresh equals 0 just in order for the Stan posterior simulation output to be omitted, which is useful whenever you're working in R Markdown and don't want the whole convergence output to be part of your Markdown document. Okay. So this is quite similar to our GLM specification, of course, and if we look at the underlying coefficients, they're obviously very similar as well. Minus 1.45 for the intercept and 0.26 for income, for the coefficient for income. We have minus 1.5 for the intercept and 0.3 for income. Okay. So how can we interpret this coefficient? Okay. First of all, the first step, of course, is to kind of think about the direction of this relationship. So positive coefficient indicates that an increase, or if we compare two groups of respondents, one with a higher income level than the other, then the probability of voting, so the probability of one, which is in this case the probability of voting for a Republican candidate, is equal to is larger. Okay, so an increase in income is associated with an increase in the probability to vote for the Republican candidate. Okay, so that's the first step, right? We can look at the sign of these coefficients and say, okay, an increase, or if we think about it as comparisons between groups of observations, the group of observation with larger values in the predictor also tends to have a larger probability of a 1 rather than a 0 in our outcome measure. Okay, so that's the first step. In terms of directly interpreting the coefficient itself as a probability, it's not as simple as the linear probability model, right? Because we have to take into account this link function, right? On the one hand, of course, that makes it a little bit more complicated, a little bit less straightforward, because we can't directly say a 1 unit increase leads to an x, change in the probability of observing a 1, because that change in probabilities now is not linear anymore, right? Because it is basically a change in the, you could think of the change in the underlying latent variable, which is then translated into a change in probability, and the change in probability itself is not constant anymore, right? So that makes it a little bit more complicated in some ways, but we overcome this issue of out of bounds predictions, okay? But we'll see in a second that there is an equivalence, or in many cases, the answers that we get from the linear probability model and the logistic regression model is actually quite similar for reasonable ranges within our predictors, okay? One simple kind of rule of thumb we can use to kind of get an idea of the underlying effect size is the rule, the divide by 4 rule that is mentioned in the textbook, okay? The idea behind the divide by 4 rule is basically that the coefficient, roughly the coefficient of the Logit, or the Logit coefficient, right? If we divide the Logit coefficient by 4, the result is roughly approximates the largest change in probability for 1 unit change in our predictor around the range where the probability is equal to 0.5. So remember this nonlinear logistic curve or nonlinear Probit curve, where obviously at the upper bound and lower, or for very small ranges of for very small values of x or very high values of x, there's a very small change in the probability because we're close to 1 or close to 0. But right in the center, this is where kind of the slope of this link function is highest, right? And so if we divide our coefficient by 4, that approximates the slope or the change in probability around this point where this change in probability is highest, okay? So one way we can think about this is if we have a coefficient like 0.3 or 0.26 that we had when we estimated this in using GLM, is that beta, or 0.3 divided by 4, is the maximum difference in the probability of observing a 1 corresponding to a 1 unit increase in x, okay? So dividing the coefficient by 4, so this is in our case 0.26 divided by, or 0.3 divided by 4, something around 0.6 or something like that, or probably 0.07, 0.08, something along those lines, 0.075 or something like that. That is basically that is an approximation of the largest probability increase that we observe when kind of in the mid-range, when the probability of observing a 1 is around 0.5, okay? This sounds a little bit abstract, but it gives you a little bit of a better kind of intuition as to how large these effects actually are, right? We can divide the coefficients by 4, and that's the kind of approximation of the maximum change in probability that is associated with a 1 unit increase in x, okay? To kind of also kind of show this visually, I mentioned we can of course graph the fitted model for for the data that we observe, okay? So these are now based on our estimated STAN model. We have our fitted logistic regression, which kind of shows this curved link function where we get close to 0, this becomes less steep, and when it becomes closer to 1, it also flattens out. And we see that the increase for every 1 unit increase in x, the probability of observing a 1 is not constant due to this link function, right? But basically around this, like right in the center of our data, where this slope is steepest, right? This is where the probability increase for 1 unit in x is kind of approximated by 0.3 divided by 4, essentially. Okay. And one thing to note here also is that I didn't only, and again, the code to produce this plot is included in the lecture code for on RStudio Cloud, so make sure to go through that code as well. You will see that I included 2 different components. One, I included our estimated Logit fit in our scatter plot, but I also included the basic linear regression, basically the linear probability model that we estimated in one of the previous videos. And one thing that you see right here is that, at least in this case, where we have probabilities that are ranging between 0.5 and 0.25, that this linear probability model, that's this blue line, despite the fact that we make these assumptions about modeling the probability directly in a linear fashion, actually approximates the Logit results quite well, right? So within this range of income ranging between 1 and 5, there's actually quite the overlap between our linear probability model and the predictions based on the linear probability model and our Logit fit. Okay. Of course, if we had a wider range of income, this wouldn't work quite as well, because as soon as we get closer to 0 or closer to 1, this linear fit would of course just continue linearly and result in predictions smaller than 0 or larger than 1, while our Logit link of course does not is bound between 0 and 1. Okay, but for outcomes that have probabilities that are, between 0.25 or vary between 0.25 and 0.75 or something like that, the linear probability model actually does quite well. Okay. Okay. So we'll talk about more examples in the Q&A session, and we'll talk about more interpretations. But at least for now, the first thing you can think about is the direction of these associations. Again, keeping in mind that these are not causal relationships, but these are just comparisons between groups of observations and expectations conditional on our predictors. Then we can kind of roughly get an intuition about the probability increase for 1 unit increase in, or the maximum probability change for 1 unit increase in x by dividing our coefficient by 4, which is basically approximating the slope at the point, or the slope where this Logit curve is basically steepest. Okay, so this is usually kind of somewhere in the center, close to where the probability is equal to 0.5. So that would be right here. And then for any additional substantive interpretation, ultimately what we'll have to do is we have to compute directly the probabilities rather than relying on our coefficient and our linear predictor. So we basically have to plug them into our link function and actually compute our quantities of interest to give it a more exact substantive interpretation. And in order to do that, if we're using Stan for our estimation, we actually have basically directly a large set of simulations and a large set of quantities that we can directly generate based on our simulated draws from the posterior distribution, right? And this is again one of the reasons why or one of the advantages that Stan or the Bayesian inference framework has over the classical framework is because it's very straightforward to directly extract these quantities of interest and directly compute underlying probabilities or predicted outcomes, while taking into account the uncertainty around our estimates, or taking into account even additional uncertainty regarding individual predictions and so on. Right? We talked about a lot of these techniques in the context of linear regression already, and basically we can use exactly the same commands for our Logit models as well. Okay. So as I mentioned, the benefit of Bayesian inference, even if we use non-informative priors, is that we can use these simulations from the posterior distribution, not just a maximum likelihood point estimate and maybe a standard error, to directly summarize this uncertainty and make probabilistic predictions that are actually substantively meaningful. Okay. So, for example, based on our model, we can directly predict, for example, vote preference for specific values of our income measure. If we use the predict function, we can directly get a prediction. Here we just have one observation, or our new data frame consists of just one observation with income being equal to 5. If we do use our predict function with our model object, we can directly compute a predicted probability of observing a 1 for that specific income level. Just note here that we have to include this option type is equal to response. If we don't include this option, then this will not be a predicted probability, but it will actually be the prediction in terms of the linear predictor. So basically before plugging it into our link function. Okay. We can also, of course, this we can also do based on our standard GLM model output, but of course we want to quantify the uncertainty around our predictors. Okay, and we mentioned a couple of weeks ago when we introduced these ideas in the linear regression framework that we can use the commands posterior underscore linpred to basically compute the linear predictions or the linear predictor with uncertainty. We have posterior epred for the expected outcome with uncertainty, as well as the predictive distribution for a new observation using posterior predict. Okay, and in the OLS context, we talked about these, specifically the comparison between posterior predict and posterior epred, to take into account different levels of uncertainty, right, between basically just predicting averages versus predicting individual observations, which incorporates more uncertainty, right? But here this is a little bit more complicated because we have kind of this difference between our linear predictor, the systematic component, then plugging that into the link function to actually get our probability, and then our individual predictions, which are again kind of dichotomous outcomes, right? So here, if we use posterior linpred, ultimately what we get is our linear values for our linear predictor, taking into account the uncertainty around our coefficient estimates, right? So obviously this is not bound between 0 and 1 because this is not a probability. This is just the beta prime xn linear predictor that we plug into our link function, right? If we want to get our resulting probability, we have to either directly plug this into our link function, or we can directly use posterior underscore epred, which then gives us the expected outcome. And the expected outcome, of course, is equal to the underlying probability of observing a success, right? So 0.46, 0.48, 0.51, and so on. And these would be, this is just the first three elements of this vector, but of course we have 4,000 in using default settings. We have 4,000 draws from the posterior distribution, so we have a distribution of probabilities, taking into account again the uncertainty around our estimates. Okay. Now, if we use posterior predict, what we do in addition is not only do we compute the predicted probabilities or the expected outcome, but we actually take a draw from that binomial distribution for each individual observation, right? And so rather than having probabilities as drawn from this posterior distribution, or probabilities conditional on what coefficients we drew from the posterior distribution, we actually have individual predictions of 0 or 1, right? So this takes into account additional uncertainty for individual observations, for individual predictions, because we're not just computing the probability, we're actually computing then whether this, coin flip turned out to be a 1 or a 0 based on the probability that was 0.46 and so on. Okay, so those are all different commands that allow us to compute certain quantities of interest while taking into account different levels of uncertainty, similar to the way we did it in the OLS context. Okay. We can, of course, in this example, I just showed you this with a single input value, so income just being equal to 5. We can, of course, use like ranges of input variables and think about different types of scenarios where we want to compute different quantities of interest. We can do this just by specifying a different or additional observations in our data frame that we use either for predict or posterior linpred or posterior epred. The same rules apply. We just, rather than just getting one column of probabilities or one column of linear predictors, we now get multiple columns corresponding to each of those different values that we set in our new data frame. Okay, but again, we'll talk about those examples in our Q&A session. Again, for posterior predict, this will then be a vector of zeros or ones, because we take into account the uncertainty in predicting individual outcomes, and therefore not only just compute the underlying success probability, but actually flip the coin and say, okay, this one landed on heads, this one landed on tails, and so on, right? All that being said, of course, these uncertainties or being able to directly take into account these uncertainties is extremely useful, because it allows us to make direct probabilistic statements based on our models. So for example, we could compute something like the 95% posterior distribution for the difference in the support for Bush, comparing people in the richest to the poorest category, right? So this difference we could just compute based on the quantiles of the difference between the predicted probabilities or the expected outcome for the highest income category minus the lowest income category. And so the difference in support for Bush comparing the richest and the poorest income categories is between 14 percentage points and 32 percentage points, or between the probability of 0.14 and the probability of 0.32 to support Bush as compared to Clinton, right? This is just one example where we have we start with a rather abstract Logit model where we can't directly compute the coefficient or substantively interpret the coefficients in a meaningful way, but we can directly summarize the quantities of interest and make a clear probabilistic statements about the actual implications of this model while immediately taking into account the underlying uncertainty. And this is just one example. Okay. One thing that we'll talk about more in the Q&A session as well is to evaluate model fit and predictive accuracy. Again, these things are similar to kind of some of the techniques that we introduced in the context of linear regression. We can estimate within sample predictive accuracy, kind of the basic naive way, or the kind of the first cut of this predictive accuracy could be to just average the predictive probabilities or average the predicted probabilities of observing a 0 and observing a 1 across all observations that actually were a 1 or actually were a 0. Here we would get, for example, 0.351 and 0.644. This means basically the average probability of predicting a 1 among observations that turned out to vote for the Republican candidate is around 0.35, and the average the predicted probability, the average predicted probability for among observations that voted Democratic was around 0.64. Okay. So this gives you a first idea of the within sample predictive accuracy. Obviously, if this is close, if both of those are closer to 1, then we're basically more certain to correctly predict ones and zeros the way they are, like within sample, the way we observe them, right? So this is kind of one first way of estimating within sample predictive accuracy based on a dichotomous outcome. But we have other measures for predictive performance. One measure that we talked about was using within sample log scores. Basically in the context of dichotomous outcomes, this within sample log score basically consists of taking the logarithm of these predictive probabilities for observed ones and observed zeros. Okay, and this is basically just a transformation of these average predicted probabilities. Okay, if we do this for the ANES 1992, we compute we get a average within sample log score summing basically over the zeros and the ones, the actual observed successes and the observed failures. We get a log score of minus 714.5, which in of itself doesn't really have a clear meaning in an absolute sense, but we can compare it to a predictive performance based on just a coin flip. That was one way that this is kind of compared in the context, or that this is discussed in the textbook. But we can also use it for comparison between different model specifications. Okay. Of course, this is still kind of based on within sample predictive accuracy. And of course, ultimately, in order to avoid overfitting, we might want to examine these predictive performances using cross-validation, for example, leave one out cross-validation, right? And so this goes back to our expected log posterior density using leave one out cross-validation that we already introduced in the linear regression framework. And it turns out this is basically an equivalent, or you can think of this as a similar measure to the within sample log score that we kind of manually computed here, just computing the same quantity based on for the leave one for the left out observation. So directly kind of taking into account potential overfitting. Okay. But again, I'm kind of going through these quickly in this video. We'll talk more about specific applied examples in the Q&A session, so you have a little bit more kind of live coding experience using these measures. Okay. Just lastly, before I finish, I just want to show you one quick explanation, or one quick justification of why we go through the trouble of using stan rather than just the base RGLM function. One thing that we already discussed is this advantage of being able to directly account for a certain uncertainty and using these simulated draws from the posterior distribution to quantify uncertainty in different quantities of interest. But an additional advantage that we discussed in the past is that we can use priors or include prior information, right? And even if we do have kind of weakly informative priors that just keep our estimates in kind of a reasonable range, they can nevertheless be useful in certain cases where basic, conventional Logit and Probit models run into trouble. One of these examples where the conventional Logit model runs into can cause issues is when we have what is called perfect separation. Okay, perfect separation occurs when basically one predictor perfectly predicts either ones or zeros in our data, right? So if you have, for example, just imagine you just had two income categories, but everyone who belongs to the higher income category votes one way rather than another. Okay. In cases like this, where you have such perfect separation, then the conventional maximum likelihood, Logit, and Probit are essentially not identified. And if we have near perfect separation, we can get extremely large coefficients and extremely large standard errors for our Logit coefficients. Okay. And the benefit of having weakly informative priors in STAN is that this will help resolve this issue of perfect separation, because it keeps the predictors, it keeps our coefficients within reasonable range. Okay, so based on the data that we talked about in this example, and that is also discussed in the textbook, one kind of example that you can show where you can kind of show this issue of perfect separation is if you examine voting behavior in the 1964 presidential election, and you just include three separate predictors: gender, race, and income. And we use a basic Logit model using GLM, and we'll see for race, African Americans, very large negative coefficients with a standard error of 420. Okay, so this is due to the fact that basically in this case, just due to the sample, maybe it was a small sample, maybe the nature of the election, none of the African American respondents in this sample actually voted for the Republican candidate. So basically the model breaks down, and we have a huge coefficient, negative coefficient, with a huge standard error. All right. If we estimate exactly the same model with STAN, just using default weakly informative priors, that basically keep our coefficients in a reasonable range, we have a still negative coefficient, obviously, because African American respondents were less likely to vote for the Republican candidate, but this is in a much more reasonable range and with a much smaller standard error. Instead of 420, we have a standard error of 4.27. Okay, so this is just one example, particularly if you work in cases where you have small sample sizes. If you work in comparative politics or international relations, you often have data sets with small numbers of observations where perfect separation can be a substantial issue. And in these small sample cases, conventional maximum likelihood Logit can be biased, and particularly with perfect separation can even be unidentified. And so cases like that are examples where going Bayesian and using this Bayesian framework directly gives you the advantage of still being able to estimate models that are actually useful for prediction. Okay. And so with that, I'll leave it at that, and we'll talk more about the actual applications and actual examples in our next Q&A session. All right. Looking forward to our meeting on Monday.